All right, how will we deal with the standard deviation? So the discussions of the last couple days have focused on the median ground motion. So where are things centered? But we also have to capture the full range of the ground motions, and it's really those upper tails of the ground motion distribution that we are most interested in for hazard. So the approaches that we're going to talk about and how we handle the standard deviation, there are a couple of or three approaches that we can be using. There's a traditional standard deviation, and the model comparisons of standard deviation that were shown yesterday, and also when we talked about phi versus phi-SS in the last couple of days. Phi was using the traditional standard deviation that is published in ground motion models, and that treats some of the systematic site and path terms as aleatory variability, as randomness that we don't know. That's really the penalty for modeling an earthquake by magnitude, modeling wave propagation by distance, and modeling site response by VS30 and depth. So those simplified descriptors to try to model those effects lead to variability. That's the penalty for simplicity. So moving forward, what you'll hear Linda talking about are single station sigma. So that was the phi-SS sensitivity that Nick had shown. What that does is it removes the systematic site effects from the aleatory variability. So a site has a site response that's repeatable, an average term. And we capture that somewhat with our VS30 scaling. We can tell the difference between soil and rock, on average, but we can't identify the details of this rock site versus another rock site which have the same shear wave velocity. But we know those differences are there. It's something that's knowable. As we start to get our new data sets, we now have data where we have ground motions. Here it said we need the ground motion data with multiple recordings at a site. So if I have 10 or 20 recordings at my site, or 2 or 3 in some cases, whatever it's going to be, I can start to look at the average value of that residual for the site and determine what is the actual site response, what is the repeatable part of the site response. Okay, so when we do that, we would take that then out of our ground motion model. If you want to think of it as our ground motion model now, we would have every site has its own special term that would be attached to it. So that reduces the variability because we now fit the data better. And we call that our single station sigma. The penalty for that approach, though, is that now we also have to consider the additional epistemic uncertainty that we have the right site factors. And that's going to depend on the amount of data you have. If you have 30 recordings, you may say, I really know that site factor well. If I have a small number of recordings, I need to then broaden that uncertainty. If I have no recordings, I have even larger uncertainty, and that's often the case, that I might not have a specific recording. But I can also use geotechnical site response modeling to get at it. So if I have a measurements of the shear wave velocity there, and instead of just using VS30, I now have the whole profile, and I can start to model that effect. I can do that, but it still has to capture the uncertainty. The other approach is going further, we call single path sigma. And so now we're going to not only remove the systematic site effects, but the systematic wave propagation effects. So I can see earthquakes in one region coming to my specific site, sample the same parts of the crust over and over, and there is an average difference in that 3D wave propagation compared to our model based simply on distance. Okay, so that lets us do refining of that. So really this is like very fine regionalization of the Q terms, if you want to think of it that way, but it's also of the geometrical spreading. So this requires that we have ground motion data from multiple recordings at our site with similar paths. So multiple earthquakes in one area recorded at my site. Okay? And so this lets us now remove that part of the variability, that repeatable systematic effect of the crust from our standard deviation, and we have a reduced now aleatory variability. So we're taking out things that are truly epistemic, that have been treated as aleatory for sort of convenience, and separating them out into this part. Again, we have the penalty of additional epistemic uncertainty. Do we have enough data to constrain this path effect? If we have a lot of recordings, we can get there, or you may be able to do it with numerical simulations if you have a good model of the 3D crust. But then it's going to depend on the reliability of that data and the number of recordings that you have. So as we go from the traditional approach to either of these two approaches, there is this additional epistemic uncertainty that must be brought along. You don't get something for nothing in this business, right? So the penalty of this improved model of the aleatory part is now we need to do a better job on modeling the median ground motion, and that's what these things are starting to adjust. And these will improve with time as we get more and more data, but this framework lets us start to take on that problem and use data as it comes in. I may have sparse data in one area where I can only partially constrain these effects, and in another area I may be able to do a better job. So many of you have seen this picture before, okay? This is a pretty bad looking one. We're just mainly talking about breaking our variability into two terms here. This is a standard thing that the ground motion models are doing, a variability of the average effect of an earthquake. This is this delta B term here, and it has a standard deviation of tau. So when we were talking yesterday about phis and taus, the tau is the difference from one earthquake, an actual recording, its average value, compared to what we think happens just for that magnitude. So this corrects for our oversimplification of the earthquake source process by a single term magnitude, and we get a variability tau. The other part then is within that, if I go to one earthquake and I correct the ground motion model so that it is now centered for that particular earthquake, what's the variability within that earthquake? And we call this the delta W's, and that has the standard deviation phi. So those are the two parts we've been talking about, phis and taus. Previously, we used to call those phis and sigma, and then we also used sigma for the total, and students really got confused, and not only us when we talked about, you mean sigma or what? So I think, for example, Dave Bohr yesterday was using the term sigma where we are talking about phis. So just to keep ourselves straight, we want to use tau and phi for the within, the between event variability tau and the within event variability phi. What we're now talking about, so most of the GMPEs have this information. We had some discussion yesterday, I think from Sinar Akar, getting the numbers broken down into the two components instead of having just the total. Okay, but now we're going to talk about breaking these things down further and pulling out those repeatable side effects and pulling out those repeatable path effects. So that's going to end up changing these values, in particular the phi. The phi term is bigger than tau, okay, which means it really is the more controlling feature for our ground motion models. So equation, all right. This is the only ones we're going to put up, but so our traditional approach on the top, we take our residual, our misfit of our observation to our model, and we break it into two terms. One that's constant for the earthquake, and the other that's within the earthquake. So that delta BI accounts for the correlation of the data, that all of the recordings from one earthquake might be systematically high or low. And the other part then is the variability once we correct for that correlation. We're now really going to focus on breaking that within event variability into these three pieces. Normally in the standard GMPEs, they're all merged together, but we have on the left-hand side a variability term here. This is just our, what we think is true randomness, and this is our phi for a single path. So if I know the path at my particular site, this is that variability that's left. This is the difference, or the phi, and we put path to path. This is truly an epistemic uncertainty. This is just telling me how much those path terms vary in my data set. Okay. This is the site-to-site variability. Again, it's truly epistemic, and this is telling me how much the average site response and how it differs from just our VS30 prediction of site response, how that varies from site to site in our data set. When we talk about single site components that Linda's going to be talking about, we would put these two pieces together. So we'd only pull this term out, and we'd still leave these in there, so that's the single site. If I pull both of these terms out, then I'm going to be talking about phi single path terms. So Linda's going to go through models of what this is. We have now more and more data sets around the world with lots of recordings per station that let us pull this term out and get it out of the aleatory variability and treat it in the right way as epistemic uncertainty. We have a lot fewer data or earthquakes that we can really use and pull these out. Okay? But on the Arizona site, because we're going to be looking at a specific paths from those distant California earthquakes to Palo Verde, we're going to have an opportunity to try to work this way as well. So the expected approaches to our standard deviation. For Diablo Canyon, we're looking at the single station sigma method, and we're going to be looking at estimating our site terms and the epistemic uncertainty, because both of those have to be there, with two approaches. One, standard geotechnical modeling of site amplification, and the other using observed ground motion data at Diablo Canyon. So one advantage of being in an active region is you get recordings from earthquakes, and so that we can actually now empirically calibrate our site amplification rather than just relying on model predictions of those effects. For Arizona, we're going to be looking at, these are recordings, earthquakes in the NGA West 2 data set here in Southern California. These are recordings from our locations of the TA, the U.S. array that came through here. And so we have recordings from earthquakes down in the southern end, which is going to be one ray path, and then earthquakes further to the north, which would be another ray path, and those will represent the main wave propagation effects that we're expecting, or that are controlling the long period hazard, for example. And so by doing that, we're going to be able to use these recordings from these events here. And this is a list of these events. So those of you who know your NGA earthquake IDs, most of these are the Elmira Kukapa is up at the top, okay? And these are what is called our small magnitude data set that we added in. So a big part of the reason for adding in all that small magnitude data to the NGA set was to allow us to do these kinds of calculations for removing the site terms and removing the path terms. If we just use big earthquakes, we don't have enough. So we've got to be using small earthquakes to get enough data. So you can see the magnitudes here are running, one large one, 7.2. So most of these are going to be magnitudes 4 to 5. So the expected approaches for sigma for Palo Verde is we're going for local sources. We're going to be looking at the non-California sources, not those two paths. Single station sigmas with the site term and its epistemic uncertainty estimated with geotechnical modeling of the site amplification. So they don't have recordings on site at Palo Verde to pull out an empirical estimate of the site effect. We can build geotechnical models and a range of those to capture the epistemic uncertainty. For the California faults, we're looking at running single path sigma with global models, and also we can use the check of the Arizona data to see itself what those standard deviations are from. It's a small subset, but they're consistent with the global model. So this will give us ways of estimating the path terms from the observed ground motion data in Arizona from those California earthquakes. We have to track epistemic uncertainty, that is, how well is that constrained given the number of recordings and earthquakes that we have. And then we'll have the same, this part here in single path, we need to have both of these, a path term and the site term brought along. Okay, and I believe that's it. Questions? Adrian, you need a microphone. And Linda is here, right? I thought I saw her. Great, okay. I took long enough, so.
Adrian Rodriguez Marek from Virginia Tech. When you talk about constraining the site term, you say geotechnical characterization. However, when we look at the GigNet data, there are strong site terms also at the borehole level. So geotechnical characterization by itself does not fully capture the site term.
Right, and so we will have to have still a range above that, right? So part of this is we are only going to capture the site term from the geotechnical layer that's being modeled. And the rest has to then have enough uncertainty around that.
And you have your kappa if you have site-specific measurements of kappa. That is also part of your site.
Correct. So the kappa goes into into our rock model, and we will have uncertainty in the kappa. So those will be brought along in the rock uncertainty terms. Yeah. Other questions, Tom?
So for the high frequencies, you're assuming a log normal distribution variation about some sort of mean in the system. But then for some kinds of phenomena, especially when we think things get nonlinear, there's strong reasons to think it's not a log normal distribution anymore. And since you intend to really focus on the sigma, I mean, how logically are we going to deal with the fact that sigma is not actually going to work?
So you're asking about the form of the distribution. And
In particular, we see these things that are called slap down phases that seem to occur when you have probably large velocities of the ground causing possibly separations in the geologic layers, give you extremely weird looking accelerations, high accelerations, and you'd only see those in really large velocity records. And I can't imagine how a log normal distribution would ever capture that.
So every time we've tried to check these data, even using subsets of larger data, which gets smaller, which is our problem, right? We haven't been able to see a systematic deviation from log normal where we can say the log normal model is rejected. So the part of this is in, well, could some other model fit that model as well? The hazard, so we're back to what's going to control the hazard. At the 10 to the minus 4 level, we're going to be in the number of standard deviations of probably 1 to 2 is what's going to be controlling it. So epsilons of 1 to 2, other than the distant California earthquakes. I think that one, because they're so frequent, may get us above epsilons of 2. But now we're at hundreds of kilometers away, and I'm not sure the features you're talking about would propagate or would be seen at those larger distances.
At large distances, I'm sure you're correct that this is just going to go away. I mean, this would be an issue for Diablo
right.
for sure, unless you admit that one of the branches for Palo Verde should be that possibly we have missed local faults there. I mean,
right, so our ground motion model for Palo Verde has to work close in as well, even though whether they've identified faults or not identified faults, it has to be working in at short distances. So anything we're doing on the standard deviation that applies at short distances, we would use at both sites.
And the other place that it's almost certainly not a normal distribution is at the very long period. So if you wanted to talk about Diablo for the longest periods, I'm not sure why it'd be relevant, but if you had some sort of sloshing modes in tanks or something like that, then the real issue is for the Hosgri faults or something like that. What's the slip on the fault next to the plant? And if you looked at that slip, I don't think there's any evidence that we know that there's a maximum with a normal distribution about the maximum. It's probably a power law.
So we could probably look at, there's a couple things we can look, we talked about the other day, the distributions of the slips from the rupture generators. Now that gets back to what's assumed in those and whether you can rely on them. I think when we look at the distribution of slips empirically, we're really limited in numbers of observations to push us out to the tails of the distribution. So I think we talked about this last time, Tom, a little bit about.
We'll continue to talk
we'll talk about
it.
So form of the distribution is something I think we do need to not simply say it's log normal and charge ahead and address what deviations in that form of the distribution could be. So we need to write that down again. I guess I'm doing the summary today, so I'll write that down for us. All right, any other questions?